The Stillness of Reality, a journey to absolute zero. To understand absolute zero, one must first redefine cold. In our daily lives, cold is a sensation, the absence of heat. In the realm of physics, however, heat is synonymous with kinetic energy. Every atom in a piece of iron, every molecule in a glass of water, and every particle in the air is in a state of perpetual, frantic motion. They vibrate, rotate, and collide. Absolute zero is the theoretical point where this internal motion reaches its absolute minimum. It is defined as 0 Kelvin, which is minus 273.15 degrees Celsius or minus 459.67 degrees Fahrenheit. The kinetic theory of matter, the temperature of an object, is essentially a shorthand way of describing the average speed of its constituent particles. In a gas at room temperature, molecules are zipping around at hundreds of meters per second. As the temperature drops, this thermal jig slows down. As a system approaches absolute zero, the energy available for these movements is systematically removed. If a substance were to reach absolute zero, translational motion stops. Atoms would no longer move from point A to point B. Vibrational motion reaches 0 point energy. Classical physics suggests all motion stops entirely. However, quantum mechanics introduces a nuance. Even at absolute zero, a tiny, irreducible amount of motion remains, known as 0 point energy, dictated by the Heisenberg uncertainty principle. The third law of thermodynamics, the quest for absolute zero, is governed by the third law of thermodynamics, which states that the entropy of a perfect crystal approaches zero as the temperature approaches absolute zero. More practically, this law implies a law of diminishing returns. To cool something down, you must remove heat and dump it into a medium that is even colder. As you get closer to 0 Kelvin, it becomes exponentially more difficult to extract the remaining energy. This is why absolute zero is considered a mathematical limit, a destination that can be viewed through a telescope but never stepped upon. It is a state of perfect order where the chaos of heat is finally silenced. The collapse of volume. In the early days of thermodynamics, scientists noticed a peculiar trend in gases. Using Charles's law, they observed that for every degree Celsius a gas was cooled, its volume shrank by a consistent fraction, 1/273 of its volume at 0 degrees Celsius. If you were to plot this on a graph and extend the line downward, you would find that at minus 273.15 degrees Celsius, the volume of the gas would theoretically shrink to zero. While real gases liquefy or freeze before this happens, this convergence point provided the first clue that there was a basement to the universe's temperature floor beyond which it is physically impossible to go. The quantum transition, when matter is pushed to the extreme fringes of the Kelvin scale within millionths or even billionths of a degree of absolute zero, the familiar world of classical physics evaporates. In our everyday experience, objects have a defined position and a predictable path. But at the threshold of 0 Kelvin, the de Broglie wavelength of atoms expands, and the rules of quantum mechanics take over the steering wheel. The emergence of the Bose-Einstein condensate. In 1924, Albert Einstein and Satyendra Nath Bose predicted a state of matter so strange it was deemed a fifth state, distinct from solids, liquids, gases, and plasmas. This state, the Bose-Einstein condensate, was finally realized in a lab in 1995. As atoms lose nearly all their kinetic energy, their wave packets begin to stretch. In a room temperature gas, these waves are tiny and isolated. However, near absolute zero, the waves grow so large that they begin to overlap and interfere with one another. Phase coherence. Eventually, the individual identities of the atoms vanish. They cease to be a collection of separate particles and instead merge into a single, giant superatom. Macroscopic quantum phenomenon. In a Bose-Einstein condensate, the entire cloud of millions of atoms acts as a single entity governed by one wave function. This allows scientists to see quantum behavior usually hidden at the subatomic level with the naked eye. Superfluidity, the frictionless liquid. One of the most visually stunning consequences of near-absolute zero temperatures is superfluidity, most famously observed in helium-4. When cooled below the lambda point of 2.17 Kelvin, helium undergoes a phase transition that defies gravity and common sense. Zero viscosity. A superfluid has exactly zero internal friction. If you set a superfluid in motion in a circular container, it will theoretically rotate forever. The roll-in film, because there is no friction to hold it back, a superfluid will form a roll-in film just a few atoms thick that crawls up the sides of a cup and drips out the bottom, seeking the lowest energy state. Infinite thermal conductivity. Heat moves through a superfluid so quickly that it behaves like a single unit of temperature. It is impossible to have a hot spot in a superfluid. Superconductivity, the perfect conduit. As atoms settle into their lowest energy states near absolute zero, the electrons traveling through certain materials also undergo a transformation. In a standard wire, electrons bump into vibrating atoms, creating resistance and heat. In a superconductor cooled near absolute zero, Cooper pairs, electrons pair up into Cooper pairs. These pairs are able to glide through the lattice of the material without colliding with anything. Zero resistance. The electrical resistance drops to exactly zero. A current could circulate through a superconducting ring for years without a power source. The Meissner effect. A superconductor will expel all internal magnetic fields. This allows for quantum levitation, where a magnet can be locked in midair above a superconducting base. The coldest natural voids. In the natural world, cold is an environmental condition. In the realm of physics, it is a feat of precision engineering. The universe is often described as a freezing void, but it is not absolute zero cold. Space is permeated by the cosmic microwave background radiation, which keeps the average temperature of space at approximately 2.73 Kelvin. The Boomerang Nebula is the coldest known natural location in the cosmos. The rapid expansion causes the gas to cool through adiabatic expansion. Its temperature sits at a staggering 1 Kelvin, making it the only known place in nature colder than the background of the universe itself. Surpassing nature dilution refrigerators, because the universe is naturally warmed to 2.73 Kelvin, reaching temperatures in the millikelvin range thousandths of a degree above zero requires human intervention. The workhorse of this endeavor is the dilution refrigerator. It utilizes the unique properties of two isotopes of helium, helium-3 and helium-4. At temperatures below 0.8 Kelvin, a mixture of these two isotopes naturally separates into two phases. Scientists dilute the helium-3 across the boundary, a transition that absorbs energy and drives the temperature down to as low as 2 millikelvin. Laser cooling, stopping atoms with light. For even more extreme experiments reaching temperatures in the nanokelvin range, scientists turn to laser cooling and trapping. It functions through the transfer of momentum. If an atom moves toward a laser tuned to a specific frequency, it absorbs the photon. The photon hits the atom with a tiny amount of momentum, slowing it down like a tennis ball hitting a bowling ball. By surrounding the atom with lasers from all directions, its movement is virtually neutralized. The final frontier, we pursue absolute zero to build a better understanding of reality. By silencing the noise of heat, we create the perfect environment for quantum computing, where qubits require extreme cold to maintain entanglement. Precision metrology. Atomic clocks are most accurate when atoms are nearly still. Fundamental testing. Searching for dark matter in an environment where the energy of the universe is at its most quiet. Oddities of the extreme negative temperature. Perhaps the most counterintuitive oddity in physics is the existence of negative absolute temperatures. In quantum physics, a negative Kelvin temperature is actually hotter than infinity. In certain quantum systems with a maximum energy ceiling, if you force more than half of the particles into their highest energy state, the distribution flips and the temperature becomes mathematically negative. Such a system wants to give away its heat with intense intensity into any positive temperature system. The speed limit of the third law. The third law creates a strange phenomenon regarding the speed of cooling. As a system approaches 0 Kelvin, its heat capacity vanishes. While you might think this makes the last bit of cooling easy, the tools we use to remove heat become less efficient at the same rate. You can reach 1/millionth of a Kelvin, then 1/billionth, but the zero itself remains an eternal horizon. Quantum pressure. Normally, if you stop the motion of atoms, you would expect them to settle into a pile. But near absolute zero, Fermi pressure prevents this for particles called fermions. The Pauli exclusion principle states that two fermions cannot occupy the exact same state, so they stack on top of one another in different energy levels. This creates a pressure that resists compression even without heat. The frozen light experiment. In 1999, researchers used a Bose-Einstein condensate to slow light down to 17 meters per second and eventually brought it to a complete standstill. By cooling a gas and using lasers to manipulate its transparency, light information can be stored in the atom spin and then released later. Practical usages and the future. The pursuit of absolute zero is the engine driving quantum engineering. Quantum computing processors must be housed in dilution refrigerators at 15 millikelvin to prevent thermal noise from destroying fragile quantum states. Ultra-precise sensing. Atom lasers created from Bose-Einstein condensates can detect changes in gravity with extreme precision, potentially allowing for GPS-independent navigation. Medicine sensors called SQUID can detect magnetic fields 1 billion times weaker than the Earth's, allowing for ultra-high-resolution brain mapping. Space-based labs. The Cold Atom Lab on the International Space Station creates the coldest spot in the known universe to test Einstein's theory of general relativity without the interference of Earth's gravity. The hazards of the void. The dangers of absolute zero involve volatile chemicals and high pressures. Cryogenic expansion. Liquid nitrogen expands 694 times its volume when warming to gas, which can cause explosions in sealed containers. Asphyxiation. Colorless, odorless gases like helium can displace oxygen in seconds. Material failure. Materials like rubber or steel undergo a ductile to brittle transition, becoming as fragile as glass. Superchemistry. Liquid helium is cold enough to liquefy oxygen from the air. Liquid oxygen is a powerful oxidizer that can become explosive when in contact with organic materials. Quenching. In superconducting magnets, if a wire warms slightly, it regains resistance, causing the surrounding liquid helium to boil violently and potentially buckle the steel housing. Vitrification. Contact with human tissue causes instantaneous vitrification, where cell water turns into a glass-like solid, shattering cellular structures. Conclusion. The journey toward absolute zero is a voyage into the fundamental stillness of the universe. While the Planck temperature represents the absolute hot of the Big Bang's chaos, absolute zero represents the absolute cold of perfect order. By stripping away the vibration of heat, we uncover the hidden mechanisms of reality. Absolute zero remains a paradox, a destination we can see but never inhabit, yet it is the quietest place in the universe where the secrets of matter are finally whispered clearly enough for us to hear. The end.